Recording in progress.
Okay, cool. So yeah, if I'm graphing this, I mean, I know it's up, right? So you're cool with my parabola? Does that make sense? So and so on. Okay. And y equals 2x. Let's do that in red. Do you need notes, Thomas?
Oh, these are good.
Oh, yeah. See, I was like, I just said,
The word on mine.
took my notes.
Yeah, man. What's going on?
I had to double check that one.
Appreciate it.
Okay, what's the slope for this line? Good. It's kind of a crooked line. But how many times is it touching the parabola? Twice. There we go. So points of intersection are super easy. 0, 0, and 2, 4. Algebraically, that's not hard. How would I solve this algebraically? Yeah. I love how I could do this with you guys so quickly, whereas my Algebra 2 class, I actually have to take my time explaining this. So, all right, but we're cool with that. Makes sense. Plugging 0 back into the equation, you get y by 0.2. So, you know, just to review, just make sure, hey, this is but we're doing this now for polar. And that's where it gets interesting. And I might need to reference the notes because there's gonna be some weird stuff happening. I don't remember where the weird stuff happens. Yes, here we go. Perfect. Okay. So far we're cool. All makes sense. All right. So let's move on. Actually, I'll just freeze in case you guys are still copying. So the bottom of the page says for graphs polar curves, a physical point of intersection from the graph of two polar functions does not necessarily indicate an actual unique point of intersection. So let's explain what's meant by physical and actual. So a physical point of intersection from two polar curves can be one of the following. It is an actual point where you see them touch. It can represent more than one point of intersection, basically kind of like a retracing in a way, if that makes sense. Or just simply not there. Doesn't make it true. It's like extraneous. So it can represent more than one point of intersection because you know, we know that some of these things retrace themselves, so we have to be mindful about that. But yeah, you know, it could be just what we see, but we have to kind of like, so physical means like what you actually see, right? We actually see, but because things get retraced, algebraically might show something else. So we're going to talk about all this as we go through the examples. The first one will be pretty straightforward though. Okay. So let me move the screen here. Here we go. Okay, cool. So and I'm going to determine the actual point. So the actual points, so just, you know, actual refers to analytical. Physical refers to graphical. Okay, just so we're clear on that, okay? So physical is what you physically, like what you actually see, but analytically is what we solve, okay? Because remember, sometimes these things retrace themselves, right? So that could happen. We have to be mindful, but then there's a redundancy that we have to be mindful about, right? Because remember, like if you had 2 comma pi over 4 and negative 2 comma 5 pi over 4, they're the same thing, right? Right, because they go back to the same place. So we just have to be mindful about that. Well, this is easy. How do I solve this one? Yeah. Well, say it can equal, guys. Yeah, done, right? So that's not that hard. So this is my answer. Test won't be that easy. That's way too easy. But let's graph it. R equals 1 is this. That makes sense? And then sine theta, ooh, that's tiny. You know, let me do this. Let me zoom in. Hopefully you guys can see that. That's not probably the best color. And then for sine, that's just gonna have a diameter of 1, right? Oh man, I just kidding. No, that's okay. So you see what's happening here? Where do they touch? They touch at 1, 5/2, right? Radius of 1 on a polar curve, angle 5/2. So all's good? Okay, cool. So that's what's happening with that one. All right, clear. All right, so that's pretty straightforward. And again, the actual point of intersection, what we solved analytically is 1, 5/2. Physically, we saw the same thing. So the analytical and graphical match each other up. We're all good, right? Okay, let's look at example 3. I'm just so excited. We're like 4 examples away from being done. New material. Love it. All right. Okay. Example 3. Just some equal to each other, right? Not that hard. Does that make sense? Sine theta equals 1. Where does that happen at, guys? Yeah, pi over 6. But truly, we have to say, if we're going from 0 to 2 pi, actually, yeah, all these are going from 0 to 2 pi, by the way. Yeah. Actually, there's no other repetition, right? That's it. Yeah, that's it. Yeah. So your answer is going to be if you plug it into either equation, what's sine pi over 6, guys? Well, 1/2, but yeah, but you have 3 halves. And then 3 halves. When you plug it back in either equation, solve for r. Because what's sine pi over 6?
1/2.
What's 3 times 1/2?
Oh, you know.
Yeah, yeah.
Okay.
Okay, that kind of encroached some space. So let me okie dokie. Well, how do I graph this? The sine theta has a raised diameter of 3. So let me put a circle there. Okay, we're okay with that? Now, next up. Do you guys remember what to do about this? Slim con, right? I mean, graph in Desmos if you want, but if I were to graph that, that's going to be down 9. So I'm gonna have to, let's go pink here. So what's the inner loop, guys? There's 1 outer loop. Oh goodness, 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah. And then let's figure out where it's touching as 0. If I plug in 0, 4, yeah, right, right.
That would be -1.
Yeah, so it kind of does this. Was that a mistake?
No, the loop goes down.
Yeah.
Oh yeah, that was done with me. Sorry, my apologies. Yes, you were correct. Yes. So it does this. Steady hands. Actually, I'm pretty good at it. Okay, I'm okay with it. All right, kind of hard to tell where they touch. It's kind of hard to tell. So you know what? I didn't quite do it the best that you could do it. Actually, I'm gonna try one more time. Okay. So 3 halves, the point of intersection, right? I should have actually labeled that first. There we go.
Does it touch up a pole?
It does.
Why is that not one of the answers?
But they don't have the same.
Oh, that's it.
That's not analytical.
Actual.
Yes.
It's not
It's
analytical.
just physical.
That doesn't make sense.
Okay. So here's the deal, guys. So these were actual, right? But physically, the 3 points of intersection, including 0,0. Because if I do plug in, yep. Right. Because here's the deal. If I plug in 0 here, right? So this illustrates why physically it's not naturally actual. Okay. What's 3 sine 0? 0. So you're gonna get the pole, right? Okay. What's 4 sine 0? Oh, sorry, if you plug in 0 here,
You get 4.
you get R equals. Yeah, you get R equals 4. But ultimately it will hit the pole when sine theta is a value of 4/5. So it does hit the pole eventually, because we hit the pole when R equals 0, right? But it happens at a different place. So yeah, 4,0 that actually doesn't count. So let me say this.
Yeah.
Yeah, including the pole. So the pole does not show up in the analytical solution. And that's just because of just the nature of 0. It's just kind of a funny situation. Because it happens at different theta values. But what you could do is go to Desmos. Desmos might be a little bit better for us here. Actually, let me do the graphic calculator. It might be better. Because that's what you're going to have access to. So we'll do 3 sine theta. And let's go,
Wait, is it in radian mode as well?
correct,
Radian and polar.
correct. Oh, 0 to 2 pi. Okay, so we got that right. Then if I graph the next one, which is 4 minus 5 sine theta. So we got this right. And I don't think it does points of intersection, unfortunately, but if you do value, if I plug in 0, so say it's 0, 0, if I hit the down key, you see it's at a different place, right? When I plug in 0 for theta, it's at 4, so it's at a different location. So that's a little tricky. If I were to go back to the home screen and solve for the zeros of the first equation, 4 minus 5 sine theta. So if I did the inverse sine of 4/5, is that right? Yeah, inverse sine of 4/5. I get 0.927. Let's store as a value. And if I go back and do alpha A. So for the first curve, it's like somewhere over there. But for the second curve, see, it's hard to tell, but it's pretty much back at the pole. Actually, let me try again. Let me do 0.927. I don't know why it doesn't see that spot on, but anyway, but you get the point, like what's happening there. So,
Pretty fun.
just by graphing. Sorry, how do you find what? The actual or the physical? All we're doing is we're just finding the actuals. That's all we're doing. And I'm just making a statement that the physical may not line up with the actuals. So, because we didn't get the poles being an algebraic solution, but it is a physical point of intersection because they do touch there because they both pass through the pole. So that obviously, but because they happen at different theta values, we don't get that coming out as a solution. So,
So it's like the actual points of intersection, when you trace them occurs at the same time, when did you like get to the same place at the same time?
not necessarily. But
Yeah, is that what you mean?
well, actually, let me think about that. Well, no, that's true. That's true because you're at different angles, right? That's what. Yeah, right. No, you're right. You're right. If you're assuming you're rotating the same speed, right? Sorry, I was overthinking that one. Okay, let's move on, guys. Example 4. So again, let's just solve this analytically. So what happens to the ones, guys? They cancel. So then you could say this. Then divide by cosine theta.
Put the negative down.
Didn't go anywhere. Just went to that side. Did I make a mistake?
Can you put a -1? It's fine.
Why not?
If you move the person over.
Yeah, divide by -1. Or multiply will by -1. Yeah. Right.
Then wouldn't it be 0 on the other side? If you go.
No, divide, not just adding or subtracting.
Oh, okay, yeah.
Yeah. I think you were trying to, were you trying to add the sign over or subtract? Yeah, don't do that because that makes it worse. I mean, you could do, actually, Thomas, you could do that. There's nothing wrong with that. If you did that, then you have this, right?
Yeah, and the sign would be negative.
And then, right, then what has to happen is that in order for that to be true, this has to equal the negative counterpart of that. But I don't want to do that because that's just too much work. I think it's just easier to say this, right? Yeah, so again, just to think about it again. Yeah, that happens at 3 pi over 4 and 7 pi over 4. Okay. So let's locate. And then when you plug those in, that's going to get a little bit nasty a little bit, but you could say the points of intersection are by plugging 3 pi over 4 into this, that'll be 1 minus √2 over 2, comma 3 pi over 4, and 1 plus √2 over 2. Okay. And then I'm going to actually do some Desmos just for interest of time.
You know which one to plug in for which one. Like, how do you know to plug in 3 pi/4 for the cosine? Why would you plug in?
Oh, you've got the same thing. Yeah, we've been same.
You plug in 3
Yeah,
pi/4?
yeah, we've been same. So it looks like you have two cardioids. And kind of hard to tell, but it looks like it's touching at 7 pi/4 there. And the race is a little hard to tell, right? And then here, that looks like it makes sense also. They do intersect at the pole again, though. Right? So when we look at the graph, they do intersect at the pole. So this happens for this happens at pi. No, 0. So 0, 0, and that happens at 0, pi/2. No, 3 pi/2. Was that? No, because cosine 3. Oh, you're right.
Yeah, 0, for cosine.
Wait,
and 0 pi.
0 pi/2 and 0, pi. Yeah, right.
It has to.
Or wait. No, it's, yeah.
No, 0 pi. Yeah. So even though they intersect at the pole again, but they happen at analytically different places. So really, you only have two actual points of intersection,
Which is one we found.
which is these right here.
Yeah, the ones we analytically.
Right. So this was 1 plus √2/2. And this was at yep. Yeah, it's definitely a race less than 1 where they're touching. So yeah, it makes sense. Okay. All right, 2 more. Okay, that's just a circle. And then you have a rose curve. How many petals will this have?
4.
Yeah, so I think we can actually do this one by hand.
And they're each 3 away.
Mm-hmm. So first one's a race of 3 halves. Okay, I think I got the circle there. And then the rose curve I'll just do by hand. Should tell Zoom to do a polar thing. How long is each one? About 3, right?
3.
Okay, I think I kind of did it right, but how many times are they touching here, would you say? Well, it looks like they're touching 8 times, right? There are 8 physical points of intersection, right? Well, let's solve it, see what happens.
And 1. Cosine 1/2 the power of 3.
Mhm.
Isn't that alternately 8 actual points because it doesn't trace itself from it because it's positive?
Yeah,
Because it's negative?
yeah, so that's it. I said, what, say it again? Yeah, we have 4 petals, right? But it doesn't retrace though, because it was even, right? Well, hold on, let's solve it. Let's see what happens. Let's solve it. So what's gonna happen here is that cosine 2 theta equals 1/2. So 2 theta equals pi over 3. Is that right? Yeah.
Yeah.
Or it's gonna be
No.
so definitely a pi over 3. Definitely have 4 pi over 3.
Don't you
Wait.
divide by
What?
two?
Oh, I forgot to divide. Yikes. My apologies. That's 3 pi over 6.
So what about the other
My
one?
apologies. No wonder you
What
guys are
about
confused.
pi?
I'm gonna get there also. Yeah, don't worry about it. I got it. So you have this. So it's yeah, plus pi k. Is that right? So you get 4 answers: pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6. So there's actually just 4 points of intersection. Physically, it shows 8. And that's just because of all the, not the retracing, but yeah, it's just it's acting kind of funny a little bit. So we do have yeah, you don't get the like the vertical ones, it's kind of weird. I'm trying to understand why that is happening, but it happens. Yeah, so it basically shows this. So you have this right here. Is that. And then this one.
Are we only going to like from 0 to 2 pi?
Exactly.
Is that gonna be like the range for every single one?
Yep. Yeah, for these notes, yes.
Then you have to plug it in to figure it out. You have to plug in.
Yeah, so these other 4 on the vertical leaves don't show up analytically.
It's just, you're gonna go like that versus that around the circle, because you like, you know how it switches off. And on.
Wait, but
Trace it and bring it.
if you algebraically plug in where it intersects at pi over 2, it like works.
If you plug in pi over 3, you have 3 cosine. Yeah, but that's gonna be negative. Oh, I know why. Okay, I see what's happening. Yeah, so it's gonna be yeah, if you plug in 2 pi over 3, you have, or let's just say you plug in pi over 3. Plug in pi over 3, you got cosine of 2 pi over 3, which is negative half. You get r equals negative 3 halves, which does send us back. Yeah, so that's the reason. Yeah, that's the reason why. You want to get these negative values. Yeah, if you plug in yeah, like if I put in 2 pi over 3, that's cosine of 5 pi over 3, which is negative 3. But
I mean, I guess technically, wouldn't they have?
Yeah.
That, wouldn't those technically be real intersections, because wherever.
they're physical. Yeah. But they're not the act, that's not what you get analytically, right?
Is it because?
Because the R values are not the same. That's why.
Oh, you're right. Okay,
Yeah. Yeah. So the reason why, actually, I'll put it right here. The reason why the other 4 physical points of intersection don't appear as analytical solutions is because
It's like 1 for the radius.
Yeah, that's what happened, guys. And I'll need to,
Oh, so the point at,
let me move that.
Right, you can-
Yeah, that's the reason why.
like, one column high.
Mhm.
And. -1,
Zero, right? They're the same. Exactly, because they're not exactly the same values for the coordinates. But this, so guys, what David said was really kind of smart. He says a lot of smart things, I know. So if you have 1 comma pi, you're right here. If you have -1 comma 0, you're back in this, you're still in the same place. They're not actually the same coordinates, but physically they're in the same place because of the 180-degree rotation. That's why we're seeing this happening. That's why we're seeing a disconnect between the actual and the physical, because sometimes the coordinates are not 100% the same, but they land in the same spot, given the fact that r is negative. So that was a great way of thinking about it. Love that. It's all coming full circle, no pun intended. All right, so last one, example 6. All right, so let's set them equal to each other again. Or let's substitute actually. That's gonna happen at pi over 2 and 3 pi over 2. And that happens at 0.
No, just.
So yeah, that's pretty simple. R0 here. And that's at 1 comma 0. And this was, I think, like kind of looks like a figure 8. Yeah, I'll go to Desmos really fast, show you the graph.
I think it's only a circle.
Hold on.
What is it called?
It's like a limit on without.
There's no way R squared equals. There's
I think so.
Oh, does it look like that because there's no 2? Oh, is it the 2? Maybe it's the 2 beta.
It's the, yeah.
This is only similar to the Australian. Also, it's like all these have 2 beta, 2 beta. It depends on how much weight it depends on the-
Or maybe if I do r equals, hold on, square root. But then you have to do its negative counterpart also. There you go. So,
Oh, because it's plus and minus.
and because of the retracing bit, so your first 2 points will meet at the pole. And the second one will be on the polar axis. So yeah, that's what's happening there. So yeah, so this right here, 1 comma 0, and these two right here are both 0 comma pi over 2 and 0 comma 3 pi over 2. Yep, all set. All right, that's it. No more new material for 2024. All right, homework.